Hello everyone, and welcome back to the Statistics video lecture series on confidence intervals. So for this video, we are going to be moving beyond constructing interval estimates for population mean, and we are going to work on finding confidence intervals for other population parameters. So for this section, we are going to be constructing confidence intervals for population proportions, which is the proportion or percentage of the population that fulfills a certain condition. And we're going to be estimating the proportion of that population using the similar processes that we have used to construct confidence intervals for mean. So for population proportion, I want to bring you back to binomial distributions back in Chapter 4. Remember that the probability of success in a single trial of a binomial experiment is denoted as P. So this P, in terms of population, is called the population proportion. So the population proportion will be the percentage of or probabilities of successes in the population. Now remember, in a binomial experiment, there are only two outcomes, success and failure. P is the probability of success. That means the probability of failure is Q. So also remember that all probabilities in a sample space need to add up to 1. So P, probability of success, plus Q, probability of failure, is equal to 1, or they add up to 100%. So what we can do is we can estimate a population proportion by taking a sample and calculating a sample proportion. So the constructing of the confidence interval is going to be a very similar idea as with mean. You would take your sample mean and you would add and subtract a margin of error. We're going to basically do the same thing to estimate a population proportion. We are going to take a sample proportion and we are going to add and subtract a margin of error to construct our confidence interval for population proportion. So as far as the symbols go for population proportion is going to be denoted as P, and that is going to be the population proportion of successes. Now, to estimate a population proportion, we're going to calculate a sample proportion, which is this variable right here, and this is pronounced P hat. No, I'm not kidding. It is pronounced P hat. So P hat, the sample proportion of successes, is going to be X, the number of successes in the sample, divided by N, the sample size. So P hat is the proportion of successes in a sample. So you take the number of successes in the sample X and you divide it by the sample size N. Now, P hat is the proportion of successes in the sample. So that means the proportion of failures in the sample is called Q hat, and Q hat is calculated as 1 minus P hat, because remember, P hat plus Q hat needs to add up to 1. So for this first one, let's say that a survey of 1,000 U.S. teens was taken, and out of those 1,372 said that they own smartphones. So what we're going to do is we're going to use that information to find a point estimate for the population proportion of all U.S. teens who own smartphones. So success in this case is defined as owning a smartphone. Failure is not owning a smartphone. So there are only two outcomes here. Smartphone, successes, no smartphone, failures. So we're going to calculate the sample proportion, which is going to be our point estimate. Just like sample mean was a point estimate for population mean, sample proportion is going to be a point estimate for population proportion. So the point estimate is going to be P hat equals X over N. So our P hat here is going to be the number of successes in the sample. Success is defined as smartphones, so 372 said they own smartphones, divided by the sample size N, which was 1,000. And yes, you can leave that as a fraction if you want to, but you can also turn it into a decimal, which is 0.372. So our point estimate for the population proportion of all U.S. teens who own smartphones is about 37.2%. So 37.2% of our sample data owned a smartphone. So the constructing of a confidence interval for a population proportion is going to basically be the same idea as with mean. So we're going to find our point estimate. In this case, it's going to be P hat instead of our sample mean. And then we're going to add and subtract a margin of error. Now, the margin of error formula is going to be slightly not slightly different. The margin of error formula is going to be very different for population proportion, because you have to keep in mind sample proportion of successes and sample proportions of failures. So the margin of error formula for populations is not at all the same as the ones for mean. So the confidence interval itself is going to be constructed in a very similar way. You're going to put the population parameter that you are estimating here in the middle. So in this case, it's going to be p. And the left endpoint of your interval estimate is going to be p hat, your sample proportion of successes, minus the margin of error. Then the right endpoint of your interval estimate is going to be p hat, sample proportion of successes, plus the margin of error. And then, yeah, this is the margin of error formula for proportions. So notice we're using z-scores again. Population proportion always uses the standard normal distribution. So population proportion always uses z-scores, and it uses the critical value zc. So we're going to actually use our inverse standard normal tables anytime we are using population proportion. So the margin of error formula is going to be the critical value zc that goes with your level of confidence times the square root of p hat times q hat all over n. And remember, this entire fraction is underneath the square root. Now, a couple of conditions that have to be met in order for you to even use this. The sample size basically needs to be big enough. So you can use the standard normal distribution and a critical value zc to calculate margin of error as long as these two conditions are met. As long as the sample size times p hat as a decimal is greater than or equal to 5, and n times q hat as a decimal is greater than or equal to 5. I should have pointed out over here that p hat and q hat are both decimals or fractions. Do not plug in percents into any of these formulas. P hat and q hat need to be decimals. Now, as long as both of these conditions are met, then we can use our inverse normal tables to find the critical value zc. So just make sure that you take about 30 seconds to check that these two conditions are met. So here is the process in words to constructing a confidence interval for population proportion. Sometimes the point estimate is done for you. Sometimes it's not. So you're going to have to pay attention to whether you have the point estimate p hat or whether you have to figure out the point estimate p hat. If you do not have p hat, you're going to have to calculate it by taking x, number of successes in the sample, and divide it by n, the sample size. Then you just have to check those two conditions, that n times p hat is greater than or equal to 5, and n times q hat is greater than or equal to 5. And remember, p hat and q hat are always decimals in any of these calculations. Then you're going to find the critical value zc that goes with your level of confidence c. You're going to use your inverse standard normal tables. Since it's a z-score, you're going back to the inverse standard normal table. Then once you have found that critical value zc, you're going to calculate the margin of error e by taking zc times the square root of p hat times q hat as decimals all over n. Then you're going to construct your confidence interval, put the population parameter that you're estimating in the middle, so p. Then the left endpoint is going to be your point estimate p hat minus e. Then your right endpoint is going to be p hat plus e. So we're going to use that same data with the teens owning smartphones that we did in the first example to construct a 95% confidence interval for the population proportion of all U.S. teens who own smartphones. So starting now, it's going to be important that you pay attention to what you are estimating. We are not estimating population mean. We are estimating population proportion p. Now from example 1, we got p hat was equal to 0.372. Also from the first example, we got n was equal to 1,000. Now while we're at it, we can always figure out what q is. So q hat, is going to be 1 minus p hat. So 1 minus 0.372 is going to give us a q hat value of 0.628. And then our level of confidence c is going to be 0.95. So let's just double check those two conditions before we go any further. So let's just check that the sample size 1,000 times the p-hat as a decimal. If you do 1,000 times 0.372, you get a value that is greater than 5. So that condition is met. Then let's just check n times q-hat. So 1,000 times 0.628 is a number bigger than 5. So that condition has been met. So since both conditions are met, that means our sample size is big enough for us to be able to use the standard normal distribution to calculate our margin of error. So next what we're going to do is we are going to find the critical value ZC that goes with a level of confidence of 0.95. So if you might remember from section 6.1, the level of confidence is going to be the area in between these two critical values, negative ZC and positive ZC. And remember, these two tails are the same, so that means that these two z-scores are symmetric. Now, to calculate the area of each tail, you're going to do 1 minus the 0.95, and then you're going to divide it by 2. So 1 minus 0.95 is going to be 0.05, divided by 2 gives you an area of each tail of 0.025. Then, if you look, you're going to use your inverse normal tables to calculate to figure out the z-score that goes with the given area. Remember, the easiest area to look up in the inverse standard normal table is the area to the left, so of the negative ZC. So if you look up 0.025 in the inverse standard normal table, you are going to get negative 1.96. And remember, since these two z-scores are symmetric, that means the positive ZC is going to be 1.96. And remember, just like we did with mean, the margin of error formula for population proportion is going to use the positive z-score, so positive ZC. So now that we figured out what positive ZC is, let us go and find our margin of error. So the margin of error formula for population proportion is ZC times the square root of p-hat times q-hat all over n. So our margin of error is going to be that ZC that we just found, 1.96, times the square root of, and I would highly recommend on your calculator putting this in parentheses, p-hat as a decimal, 0.372, times q-hat as a decimal, 0.628, all divided by the sample size, which was 1,000. Now, as long as you have that fraction inside of the square root wrapped in parentheses, you should be able to just type all of this into a calculator all at once, giving us an approximate margin of error of 0.03. So the margin of error is approximately 0.03. Now what we're going to do is we're going to use that margin of error and our point estimate p-hat to construct our confidence interval for proportion. So since this is a confidence interval for proportion, we're going to put p in the middle of our confidence interval. So on the left, we're going to have p-hat minus e, and then on the right, we're going to have p-hat plus e. So for the left endpoint, we're going to take our p-hat, which was that 0.372, and we're going to subtract the margin of error, 0.03. Then on the right, we're going to, hold on, this is illegible. So on the left, we're going to take our p-hat, which was that 0.372, minus the margin of error, 0.03. And then on the right, we're going to take our p-hat, which was 0.372, and we're going to add to it our margin of error, 0.03. So for our left endpoint, when we do that subtraction, we get 0.342. And then on the right, when we do that addition, we get 0.402. So for our interpretation, what that means is with 95% confidence, we estimate that the population proportion of all U.S. teens who own smartphones is between 34.2% and 40.2%. So this next one is going to be an example where we do not have to do any work to find q-hat, and p hat because p hat is actually given for us. So what this diagram shows is from a survey of 498 US adults, so that is our sample size, N is 498. They were asked who are the most dangerous drivers, and 71% of them said teenagers, 25% said 65 and over, and 4% had no opinion. What we're going to do is we are going to construct a 99% confidence interval for the population proportion of all US adults who think that teenagers are the most dangerous drivers. So in this case, success is defined as teenagers and failure is defined as everybody not teenagers, so the other categories. So we already have our point estimate p hat. We have the sample proportion of successes. Since thinking that teenagers were the dangerous drivers is defined as success, the point estimate p hat, the sample proportion of successes, is actually going to be this 71%, because 71% of this survey said that teenagers were the most dangerous drivers, so p hat is going to be 0.71. That means that Q hat, you can either add up the other two categories or do 1 minus P hat. So 1 minus 0.71 gives us a Q hat value of 0.29. Now N, remember, was 498, and we're constructing a 99% confidence level, so our C is equal to 0.99. All right, so the first thing that we're going to do is we're going to check those two required conditions. We're going to check that N, 498, times P hat, 0.71. If you do that on a calculator, it is greater than 5, so that checks out. Then we're going to check N times Q hat, so you're going to do 498 times 0.29, which is a number bigger than 5, so our sample sizes are big enough. That means that we can use the inverse standard normal tables to find our critical value ZC. So remember, to find our critical value, that confidence level is the area in between our two critical values, negative ZC and positive ZC. And the area in between them is going to be 0.99. So to find the area between each of the tails, you're going to do 1 minus 0.99. That will give you the area of the two tails put together, and then you are going to divide that by 2. Gives you a tail area of 0.005 for each of the tails. So this tail is 0.005, and this tail is 0.005. Easiest tail to look up is the left tail, so the easiest critical value to look up in the inverse standard normal table is negative ZC. So if you look up 0.005 in your inverse standard normal table, you get a negative ZC of negative 2.575. And then for the positive ZC, that gives us positive 2.575. Remember, the reason that we are using z-scores and the inverse normal table is because this is a proportion. Proportion always uses the standard normal tables. All right, now since this is proportion, our margin of error formula is different. So our margin of error formula for proportion is going to be ZC times the square root of P hat times Q hat all over N. So our margin of error is going to be that positive ZC, which was 2.575, times the square root of parentheses P hat, which was that 0.71, times Q hat, which was 0.29, all divided by the sample size N, 498. And as long as you have parentheses around that square root, you should be all set to just plug all of that into a calculator. You should get a margin of error of 0.052. So now we're going to construct our confidence interval for population proportion. So we're going to put population proportion here in the middle. The left endpoint is going to be formed by P hat minus the margin of error. And then the right endpoint is going to be P hat plus the margin of error. So your P is going to go in the middle, and we're going to take P hat, which was that 0.71. We're going to subtract the margin of error, 0.052. Then on the right, we're going to take our p hat, 0.71, and we are going to add to it our margin of error, 0.052. So we get our confidence interval. When you do the subtraction, you get 0.658 for your left endpoint. And then for your right endpoint, after you do the adding, you get 0.762. So for your interpretation, that means with 99% confidence, we estimate that the population proportion of all U.S. adults who think teenagers are the most dangerous drivers is between 65.8% and 76.2%. Now remember, as the level of confidence increases, the confidence interval gets wider. The higher the level of confidence, the wider the interval estimate. That is just how it is. So if you want to have a narrower and more pinpointed and more accurate estimate, but a higher level of confidence, the only way to do that is to increase the sample size. So we've done this before, calculating minimum sample size, but that formula that we had before was for mean. For population proportion, if you are given a certain level of confidence and a certain level margin of error E, then the minimum sample size N needed to estimate a population proportion is given by this formula. So the minimum sample size N is going to be P hat times Q hat as decimals times ZC over E parentheses squared. It is important that there are parentheses and that the exponent is outside the parentheses, because that entire fraction is being subtracted. Now, that formula assumes that you have preliminary estimates for p hat and q hat. A preliminary estimate would just be, a quick survey or just, past study, something like that. Some idea of what p hat and q hat should or might be before going in. Now, if you have no idea what p hat and q hat are, you have absolutely no preliminary data, no preliminary estimates, you haven't got a clue. If you have no preliminary estimates, you use 0.5 for both p hat and q hat. So this formula actually makes a difference if you have preliminary estimates or not. So for this next one, let's say that you are running a political campaign and you wish to estimate with 95% confidence the population proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the actual population proportion. So that's a given margin of error. We want a margin of error of 0.03. 3% as a decimal is 0.03, because our estimate needs to be accurate within 3% of what the actual real population proportion is. We're going to find the minimum sample size needed under two conditions. One, if no preliminary estimate is available, and two, if a preliminary estimate gives us p hat of about 0.31. So for both of these, it's going to be 95% confidence. So if you use that process to find the critical value ZC that goes with the 95% level of confidence, unlike the t-distribution where we had to worry about degrees of freedom, we don't have to worry about degrees of freedom with the normal distribution. So the ZC that goes with a 95% level of confidence is 1.96. It's the same one that we got when we did this a couple examples ago. Now, if you have no preliminary estimates, that means that you're going to be using p hat as 0.5, and you're going to use q hat is 0.5. So let's see what that does. So the minimum sample size needed is going to be p hat times q hat times ZC over E squared. So your minimum sample size with no preliminary estimates, we're going to plug 0.5 in for p hat and q hat. So we have 0.5 times 0.5 times that critical value that goes with our level of confidence, 1.96, times the margin of error that, divided by the margin of error that we want, 0.03. And then we're going to take all of that and we're going to square it. Now, as long as you have parentheses around that fraction and the exponent is outside the fraction, then, outside the parentheses, you should be able to just plug this all into a calculator all at once, so which gives us 1067.11. Now, since these are people being surveyed, you really should round up to the nearest whole number, and because this is minimum sample size, you want to make sure that you have enough people. So if anything follows the decimal point, you're just going to round up. So we need to survey 1068. So if you have no preliminary estimates available, in order to guarantee this margin of error with a 95% confidence, you need to survey a minimum of 1068 people. So you need a minimum sample size of 1068 when there are no preliminary estimates available. Now, if you do have preliminary estimates, it's going to be very different. So let's say that you have a preliminary estimate of p hat being 0.31. That means that q hat is going to be 1 minus 0.31, gives us a q hat of 0.69. So let's do that minimum sample size formula again, but this time with our preliminary estimates. So we have n equals our p hat, which is 0.31, times q hat, which is 0.69, times our critical value that goes with our level of confidence, 1.96, divided by the margin of error that we want, 0.03, whole thing squared, and then just type it into a calculator as you see it. So on a calculator, it gives you 913.02. Anytime there's anything after the decimal, you should round up to the next whole number, so you get 914. So if you have a preliminary estimate of p hat equals 0.31, that means that the minimum sample size that you need to guarantee a margin of error of 3% with 95% confidence is 914. So you would need to survey 914 people. So as you notice, if you have a preliminary estimate, you need to survey fewer people. You need a smaller sample size. Now, this isn't a small sample by any means, but it is smaller than if you had absolutely no preliminary estimates. So that is it for constructing confidence intervals for population proportions. Remember, going forward, make sure that you pay attention to the problem and make sure that you are paying attention to what the problem is asking you to estimate. If it is asking you to construct a confidence interval for mean, or is it asking you to construct a confidence interval for population proportion? So in the next section, we're going to be looking at another population parameter, so it is going to be important that you pay attention to what you are supposed to be estimating. Because as you notice, if you estimate different parameters, you're going to be using different formulas. So that is it for section 6.3. Thank you all very much for watching, and I will see you in the next video. Bye-bye.